All right, let's get into it. Imagine you have a video feed that absolutely cannot fail. I'm talking a military control room, a sterile OR, maybe a huge data center.
Right.
The signal has to go, just massive distances, and copper cable. It just can't do it.
It just failed.
Exactly. So today we're doing a deep dive into the hardware that steps in right at that failure point. It's the PureLink OLC II RX, a DVI to 2LC fiber receiver.
Yeah, and our focus is really on how this very specific device tackles that critical challenge of video distribution. We're talking about secure, high-def signals that have to be 100% reliable over extreme distances.
So break it down for us. What's it actually doing?
It's pretty straightforward, really. It takes the light signal coming in over two tiny LC fiber connectors, and it converts it right back into a standard digital video signal.
A DVI signal.
This single-link male DVI-D output, to be precise. It's essentially the crucial bridge between that secure fiber network and the monitor that's sitting on your desk.
Okay, let's talk about the distance, because that's where this thing just completely changes the game.
It really is the headline feature.
If you're running a full HD signal, let's say 1080p at 60 hertz, you're lucky to get 50 feet with a standard copper cable before things start to get ugly.
Yeah, you start seeing sparkles, dropouts, all sorts of issues.
With this PureLink solution, using what's called single-mode fiber, that same signal can travel up to 6,600 feet.
Which is, that's over a mile. It's an astonishing distance.
Over a mile.
And that alone justifies the move to fiber, right? But even if you use multimode fiber, which is, more common for slightly shorter runs, you still get an incredible 1,650 feet.
Still way more than you'd ever get from copper.
Exactly. And what's really strategic here is that across those huge ranges, the quality remains absolute. The device is fully DVI 1.0 compliant. No artifacts, no drop pixels, none of that.
Okay, so the range is one thing, but none of that matters if it's a nightmare to set up. And that brings us to the intelligence built into it.
Ah, yes. The DDC and ED-diode problem.
For anyone who's ever plugged in a monitor and just gotten a black screen, you know this pain. The source and the screen just won't talk to each other.
It's that digital handshake, right? The display has to tell the source what it's capable of. When that fails, you're in for a long day of troubleshooting.
So how does this solve it?
It has something they call virtual DDC and auto ED programming. It basically automates that whole handshake. It just figures it out for you, so you don't need a separate DDC cable or any complex programming.
So it just works.
It just works. And that doesn't just clean up the wiring, It potentially saves thousands of dollars in technician time trying to debug these issues during a big deployment.
And what about the physical install? Getting cables through tight spaces.
That's another smart design choice. The transmitter and receiver modules are detachable, so you can run the tiny, thin fiber cable through a really small conduit without a bulky connector head getting stuck. It's a huge logistical plus.
Which brings up a bigger question. Why go through all this trouble with fiber in the first place? Why not just boost a copper signal?
And that gets to the core of it all. Security.
Security.
It's the #1 reason. Fiber transmits light, not electricity. So it's physically impossible to tap into it without cutting the fiber, which, would immediately break the signal.
So there's no way to eavesdrop without being incredibly obvious.
Exactly. The security isn't just a feature, it's like a fundamental property of the technology.
Yeah.
Fiber is also totally immune to outside electromagnetic interference, EMI.
Okay, so that's where those high-stakes environments come in.
Absolutely. Military command centers where you can't risk espionage.
Yeah.
But also think about medical applications, like an MRI suite.
Right, which generates a massive magnetic field.
A huge one. And any stray electrical noise could corrupt that diagnostic data. For those applications, you need absolute data integrity. It is simply non-negotiable.
And it does all this without being a power hog or a big, heavy brick.
Not at all. It uses just 1 watt of power, and the thing weighs like 0.33 pounds. It's tiny. That small, low-power design just makes it even better for these critical installations where space and heat are always a concern.
So what you're left with is a really robust, smart, and super secure solution for sending DVI signals a very, very long way.
It really is. But it makes you wonder, given that fiber is so immune to interference, think about this for a second. What other fields, outside the usual military and medical ones, are dealing with vast distances and really sensitive data?
That's an interesting question.
Could say large financial trading floors,
Mm-hmm.
or maybe decentralized university research networks where data integrity is everything. Could they use this kind of secure long-range transport to get a real competitive edge today?
That's definitely something for you to think about. And for anyone planning a deployment, you should know this solution is backed up by a pretty solid 3-year limited warranty.